124 light years from Earth, a telescope caught a whisper in the atmosphere of another world. The signal looked like a gas that, on our planet, is almost only made by ocean life. You're gonna meet K2-18b, a sub-Neptune wrapped in hydrogen, warmed by a dim red star, possibly hiding an ocean the size of a planet. You'll see why one team of scientists says we've found the strongest hint of life ever detected, and why another team says the signal is just noise wearing a costume. If you love real science with real stakes, hit subscribe so you don't miss what comes next. Settle in. We're going hunting for a ghost. You're standing on the night side of a world you can't see from Earth without a telescope. Above you, no familiar constellations. A red star hangs low on the horizon, dim as a dying ember, but it never sets. It just sits there, locked in place, because this planet doesn't spin the way ours does. Below your feet, if the theory is right, an ocean stretches across the entire surface. No islands, no continents, just water all the way down. This is K2-18b, 124 light years away, in the constellation Leo. And for the last decade, it has been the single most watched planet outside our solar system. Here's the first thing that matters. K2-18b is big, 2.5 times wider than Earth, and about 8.5 times heavier. That puts it in a weird category astronomers call a sub-Neptune. Too large to be rocky like Earth. Too small to be a gas giant like Neptune. For a long time, planets in this size range were written off as uninhabitable. Too much crushing pressure, too much hydrogen, too strange. Then, something changed. In 2019, two separate teams announced that K2-18b had water vapor in its atmosphere. Water. On a planet sitting inside its star's habitable zone, the narrow ring where liquid water could, in theory, exist on the surface. Suddenly this oddball world became a target. Not just a target. The target. The first sub-Neptune in the habitable zone with a confirmed ingredient for life. The star it orbits, K2-18, is nothing like our sun. It's a red dwarf, smaller, cooler, stingier with its light. To get enough warmth, K2-18b orbits close, really close. It whips around its star in 33 days. For reference, Mercury takes 88. Imagine a year shorter than a month. That tight orbit does something strange. The planet is almost certainly tidally locked. One side faces the star forever. The other side faces the dark forever. On the day side, the red dwarf burns overhead without moving. On the night side, the stars don't rise or set. Weather on a world like this doesn't follow our rules. Winds would scream from the hot side to the cold side, carrying whatever is in the air, smearing the chemistry across the whole planet. And the chemistry is the point. That's what we're chasing. Because when the James Webb Space Telescope finally pointed at K2-18b, it didn't just see water. It saw carbon-based molecules, then methane, then something else. Something that, on Earth, has exactly one known source: living things. The team leading the observations, a group at the University of Cambridge led by Niku Madhusudan, has spent years arguing this world could be a Hycean planet. A new category they invented. A world with a deep water ocean under a hydrogen sky. If they're right, K2-18b wouldn't just be habitable. It could be teeming. Microbial oceans churning out gases detectable from across the galaxy. If they're right. Because what the telescope saw in 2023 and what it saw again in 2025 is now the most argued over spectrum in modern astronomy. Every bump, every dip, every line. And the first clue that something was off came from a star that barely shines. K2-18 is a star you've never seen. You can't. It's too dim. Even though it's relatively close in galactic terms, you'd need a good telescope just to find it in the sky. It belongs to the most common type of star in the universe. An M dwarf, a red dwarf. About 3/4 of every star you'll ever count is one of these, and that's where the trouble starts. Our sun is a G-type star, hot, yellow, stable. It burns its fuel at a furious pace and will live for about 10 billion years total. A red dwarf is different, cooler, smaller, stingier. K2-18 burns at about 3,450 Kelvin on its surface. Our sun burns at nearly 6,000. That temperature gap changes everything. Because K2-18 is so cool, its habitable zone, the ring of distance where a planet could have liquid water, is tight, pulled in close. On K2-18b, that means orbiting at roughly 1/6 the distance Mercury sits from our sun. You get your warmth, but you pay a price. The price is radiation. Red dwarfs are violent when they're young. They flare. They throw out massive bursts of ultraviolet and X-ray radiation, sometimes hundreds of times more intense than a flare from our sun. For the first billion years of a red dwarf's life, any planet in the habitable zone is being sterilized from above. Atmospheres get stripped, water gets split into hydrogen and oxygen, and the hydrogen escapes into space. By the time things calm down, the planet that was supposed to hold oceans might be a dry husk. This is the problem haunting every red dwarf planet we've ever looked at. Proxima Centauri b, the 7 worlds of TRAPPIST-1. All of them sit around red dwarfs. All of them face the same question. How do you keep an atmosphere when your star spent its youth trying to rip one off? K2-18 helps a little. It's old, somewhere around 2.5 billion years. The worst of its tantrums are behind it. But old doesn't mean calm. Red dwarfs flare throughout their lives. And K2-18b, 33 days per orbit, sits close enough that every outburst hits hard. Then there's the tidal lock. At that orbital distance, the planet's rotation would have slowed and frozen generations ago. One hemisphere permanently cooking, the other permanently dark. On Earth, our day-night cycle mixes weather, redistributes heat, keeps any single spot from running too hot or too cold. K2-18b can't do that. It has to rely on wind. Ferocious, supersonic wind to haul heat around the globe. Computer models suggest those winds race in opposite directions at different altitudes. A jet stream that flows one way near the surface and the opposite way high above, like 2 rivers in the sky, flowing past each other. Anything living down there would breathe weather that has no seasons, no nights, no mornings, just the red sun, always in the same spot, and the howl of global wind. Here's the twist. Despite all of it, the flares, the lock, the radiation, K2-18b kept its atmosphere. We know because we can see it. Starlight passing through it, carrying chemical fingerprints back across 124 light years to a telescope floating 1 million miles from Earth. And reading that starlight is its own kind of miracle. Here's a question worth sitting with. How do you analyze the air on a planet you will never visit, around a star you can't even see with your eyes? The answer's a trick of light, and it almost shouldn't work. Every 27 days, K2-18b passes directly in front of its star as seen from Earth. We call that a transit. For a few hours, the planet blocks a tiny sliver of the star's light. From our distance, that dip is about 1%, 1 part in 100. That's how we found the planet in the first place, back in 2015, when NASA's Kepler mission watched that dip appear and disappear on schedule. Now, think about what else happens during a transit. Some of the starlight doesn't get blocked. It goes through. It threads through the thin shell of atmosphere ringing the planet, squeezes between molecules of gas, and keeps going toward us. Different molecules absorb different colors. Water eats certain wavelengths. Methane eats others. Carbon dioxide, sulfur compounds, each one has a signature, a chemical fingerprint. When starlight passes through a planet's air, it comes out the other side missing specific colors, missing in a very specific pattern. So here's what the James Webb Space Telescope actually does. It sits at a point about 1 million miles from Earth, staring at K2-18. It collects the star's spectrum, the full rainbow of its light, spread out into thousands of tiny bands. Then it waits for a transit. During the transit, a few of those bands get slightly dimmer. The difference between transit and non-transit, that tiny shift, is the fingerprint of the planet's air. The signal is almost impossibly small. Think of a candle, 124 light years away, with a mosquito flying in front of it. You're trying to measure how much dimmer the candle gets when the mosquito's wing is in the way. That's roughly the scale. James Webb pulls it off because of its size and its instruments. Its primary mirror is 21 feet across, made of 18 gold-coated hexagons. It sees infrared light, the range where water, methane, and carbon-based molecules shine loudest. And it has 4 instruments built for different jobs. 2 of them matter most here. NIR spec reads the near-infrared, the range where the 2023 detections came from. MIRI reads the mid-infrared, deeper into warm colors, the range where the 2025 detection came from. 2 different instruments, 2 different views of the same planet, 2 different chances to confirm what's really in the air. Webb needs multiple transits to build up a clean spectrum. One transit is too noisy, random flickers in the star, tiny imperfections in the detector. All of it bleeds into the data. Stack 8 transits, 10, 20, and the pattern starts to emerge from the fuzz. The Cambridge team used transits accumulated over months to build their spectrum of K2-18b. That's where the arguments start, because stacking transits is not neutral. Different teams process the same raw data differently. They choose how to clean it, what to subtract, how to weigh the noise, and on a signal this faint, those choices matter. A molecule that looks present in one pipeline can vanish in another. Before the debate, though, came the first result. A single spectrum in 2023 with 3 molecules in it that together told a story nobody was ready for. In September 2023, the Cambridge team published what they had. 8 transits of K2-18b processed through their pipeline, stacked into a single spectrum that stretched from about 0.8 of a micron to 5 microns in wavelength. Near-infrared territory. The NIR spec instrument doing the heavy lifting. The spectrum had bumps, several of them, and the bumps lined up with specific molecules, Methane, clear as anything. Detected at 5 sigma, which means the odds of it being a statistical fluke were less than 1 in a million. A real result by any standard. Carbon dioxide, detected at 3 sigma. Less certain, but a strong signal. The odds of a chance detection here come out to about 3 in 1,000. Together those two molecules told a story. On a sub-Neptune like K2-18b, if the atmosphere sat on top of a deep hydrogen envelope all the way down to a rocky core, chemistry should have broken methane apart ages ago. Hydrogen-rich atmospheres plus extreme pressure equals ammonia and simple hydrocarbons, not the balance the team was seeing. The balance they were seeing matched something else. A thin hydrogen atmosphere sitting on top of a liquid water ocean. Exactly what a Hycean world would look like. Then there was a third signal. Small, noisy, tucked into the spectrum like an afterthought. A faint absorption feature at wavelengths consistent with dimethyl sulfide, DMS. The team was cautious about it. In the paper, they called it a tentative hint. Low statistical significance, not enough to claim anything. But they flagged it because of what it would mean if it were real. On Earth, DMS is a biological molecule, almost exclusively. Marine phytoplankton pump it into the atmosphere. It bubbles off the ocean when microbial life is doing well. Sailors know the smell. That sea breeze scent at low tide, the one that tells you you're near the water, that's DMS. Our atmosphere contains it at parts per trillion levels, steady as a heartbeat, entirely because of living things. Finding DMS on an alien planet, even tentatively, was the first time humanity had ever possibly seen a gas with a known biological source in the air of a world outside our solar system. Madhusudan and his co-authors were careful in the 2023 paper. They said the signal needed more data. They said it could be noise. They said DMS on Hycean worlds had been predicted theoretically, which meant finding it wouldn't be shocking, but it also wouldn't be proof. But the word got out. Headlines appeared. Possible signs of life. The team appeared in news programs. Madhusudan gave interviews. And across the astronomy community, the reaction split into two camps almost immediately. One camp said, "This is exactly why we built JWST. Chase the signal. Get more data. Pursue the hypothesis seriously." The other camp said, "Wait. The DMS detection was buried in noise. The error bars were huge. Other molecules could produce similar spectral bumps at those wavelengths. Methyl chloride, for instance. Or simply nothing. Just random variation in the detector." The Cambridge team made a decision. They would go back to K2-18b. They would use a different instrument this time. MIRI, the mid-infrared one. A completely different slice of the spectrum, where DMS has a different fingerprint. If the signal was real, it should show up there too. They didn't know it yet, but they were about to detonate a debate that would dominate their field for the next 2 years. The data that came back in April 2025 made everything before it looked like a warm-up. Let's go back to that tentative DMS signal from 2023 for a second, because it matters more than it looked at the time. Most of the astronomy community barely noticed it. The headlines were about methane and carbon dioxide. The DMS hint was buried in the paper's discussion section, flagged with appropriate caution, treated like a footnote. But inside the Cambridge group, that footnote was the whole point. Years earlier, in 2020, a graduate student named Anjali Pieta, working with Madhusudan, had published a theoretical paper. It asked a simple question. If a Hycean world existed, a sub-Neptune with a hydrogen atmosphere over a liquid water ocean, and if that ocean had microbial life in it, what would we see? What gases would the biology pump into the atmosphere, and at what concentrations? The answer they worked out was striking. On a Hycean world, DMS and a few related sulfur compounds could accumulate to levels thousands of times higher than on Earth. Our own atmosphere holds DMS at parts per trillion. On K2-18b, if biology was producing it, the models suggested it could reach several parts per million. 10 parts per million even. High enough for a telescope like James Webb to detect it. In other words, the team had already predicted what they should see before they ever pointed the telescope. And when that faint 2023 hint showed up in the right place on the spectrum, at roughly the right strength, it wasn't random. It matched the prediction. That doesn't make it real. Predictions can be self-fulfilling in data analysis, which is one of the things critics pointed out later. You can find what you're looking for, even when it isn't there if you're not careful. But the prediction did something else. It gave the team a reason to push harder, a reason to fight for more telescope time. Getting time on the James Webb Space Telescope is brutal. Scientists submit proposals. A review committee ranks them. Most get rejected. K2-18b had already been observed in near-infrared, so the team made the case for a mid-infrared follow-up. Different instrument, different wavelengths. A genuinely independent check. MIRI, the mid-infrared instrument, looks at light between about 5 and 12 microns. Warmer colors, deeper infrared. In that range, DMS has a different and stronger absorption fingerprint than it does in the near-infrared. Methane does too, but its pattern is distinguishable. If DMS was really on K2-18b at parts per million levels, it should show up as a specific series of bumps and dips in the MIRI spectrum, at specific wavelengths, at a specific depth. The team got the time, they got the observations. 8 more transits, this time through MIRI. Months of data reduction, more months of modeling. The paper was submitted to the Astrophysical Journal Letters in early 2025 and accepted in April. When the results came in, they stunned the team. The MIRI spectrum didn't just show a faint hint, it showed a strong feature. A bump that matched DMS, another that matched dimethyl disulfide DMDS, a cousin molecule, also produced by life on Earth, also predicted by the Hycean biology models. The statistical confidence on this one came out to 3 sigma. A 0.3% chance that the pattern in the data matched the DMS-DMDS model by random chance alone. That number was about to become the most argued over 3 sigma in the history of exoplanet science. You've smelled dimethyl sulfide. You just didn't know it had a name. Walk along a beach at low tide, inhale that slightly funky, slightly briny, slightly organic smell that hits you when the mudflats are exposed. That smell is DMS. It's the reason the seashore smells like the seashore. Our nose can detect it at concentrations as small as a few parts per trillion. We're walking around with a biological DMS sensor in our face, and we don't even know it. Chemically, DMS is about as simple as organic molecules get. 1 sulfur atom, 2 methyl groups attached to it. That's it. The formula is CH3, 2S. It's lighter than water, oily, and volatile, which means it evaporates fast. In nature, it leaks out of ocean surfaces, forest soils, and marshland. But leaking out and being produced are two different things. Everywhere DMS shows up in significant quantities on Earth, you can trace it back to one source: life. Specifically, marine phytoplankton. Those tiny single-celled organisms that float near the ocean surface and do most of the photosynthesis on Earth. Many species of phytoplankton produce a precursor molecule called dimethylsulfonopropionate, or DMSP. They use it to regulate their internal chemistry, a kind of cellular antifreeze and pressure valve rolled into one. When the phytoplankton get eaten, or when they die, DMSP breaks down into DMS. The gas escapes the cell, bubbles up through the water, and vents into the atmosphere. The scale is staggering. Earth's oceans release somewhere around 20 to 30 million tons of DMS per year. It's the single largest biological sulfur source on the planet. Every breath you take near a coastline, you're inhaling trace molecules of a gas that was inside a dying algae cell days earlier. DMS doesn't just vanish once it hits the air. It reacts with hydroxyl radicals in the atmosphere and breaks down into sulfate aerosols. Those aerosols become the seeds that water vapor condenses around. They help form clouds. In a real sense, marine life is partially responsible for the pattern of clouds over the world's oceans. A microbial breath, on a planetary scale, that changes the weather. The reason DMS became interesting for astrobiology is this feedback loop. It's biological. It's abundant. It's volatile enough to reach the upper atmosphere. And it has a distinct infrared fingerprint that a telescope can, in principle, detect. For decades, astrobiologists have debated which gases count as biosignatures. Oxygen alone isn't enough. It can form abiotically through ultraviolet splitting of water. Methane isn't enough either. Geology can make methane. Even the two together, oxygen and methane in disequilibrium, which was long considered the gold standard, is now under question. Every molecule that life uses on Earth can, under the right conditions, also be made by non-life. DMS was different. At least that was the claim. Researchers looked and could not find a significant non-biological source on modern Earth. A tiny bit is produced by volcanic outgassing, but essentially nothing at scale. If you saw it in a planet's atmosphere at high concentrations, the argument went, you had probably found life. That was the argument. And when Madhusudan stood in front of a press conference in April 2025 and said no known non-biological process produces DMS at the levels they had detected, he was leaning on that argument with his full weight. The first cracks in it were already forming. Picture the ocean under you turning green. Not a single green, but a patchwork of greens and blues and coppers, stretching from horizon to horizon. You're looking at a phytoplankton bloom. Billions of cells per gallon of water, so thick the ocean changes color. So vast you can see the bloom from orbit. Satellites map these events routinely. In the Gulf of Maine, off the coast of Namibia, around the Southern Ocean, every spring, the planet breathes green. And with every bloom, DMS pulses into the sky. This is the model the Cambridge team had in mind when they talked about K2-18b, not intelligent life, not complex life, nothing like animals or plants or anything you'd recognize. Just something equivalent to a microbial bloom happening in a warm alien ocean, pumping sulfur compounds into a hydrogen atmosphere at a steady rate. No civilization required, just biology doing what biology does, metabolizing, dying, releasing byproducts. For that picture to work, K2-18b needs an ocean. It needs that ocean to be in contact with an atmosphere. And it needs some kind of self-sustaining chemistry in the water, the kind that could in principle support single-celled organisms. The Hycean hypothesis covers the first two, a global ocean under a hydrogen envelope, tens of miles deep or more. At the top, the atmosphere is cold. At the bottom, the pressure is enormous, the temperature is hot, and the water probably transitions into exotic phases. But somewhere in the middle, in what researchers call the mixed layer, conditions might allow liquid water at temperatures where biology on Earth is comfortable. Warm, dark, rich in dissolved gases. What would live in that layer? Nobody knows. It would have to tolerate a hydrogen atmosphere above it, rather than our oxygen-rich one. That isn't impossible. On early Earth, before photosynthesis flooded the air with oxygen, our ancestors were anaerobic microbes, thriving without it. Some modern bacteria and archaea still do. Extremophiles on Earth survive pressures and temperatures that should kill them. The biochemistry of alien microbes is wide open. What matters for the telescope is not the biology itself, but the waste gas. If something is metabolizing sulfur down there, or simply producing DMS as a byproduct the way our phytoplankton do, the gas escapes the ocean, rises through the atmosphere, and accumulates. Unlike on Earth, where the oxygen-rich air destroys DMS within a day or so, a hydrogen atmosphere wouldn't break it down nearly as fast. The models suggest DMS could build up for years, maybe decades, enough to reach those telescope-detectable parts per million concentrations. That's the chain. Life, to metabolism, to DMS in water, to DMS in air, to a spectral bump in an infrared telescope 124 light-years away. Every link in that chain is contested. Whether K2-18b has an ocean at all, whether the ocean could support life, whether the biology would produce enough DMS, whether the atmospheric chemistry would let it accumulate, whether the telescope is really seeing it, whether the detection is statistically sound. A chain this long breaks in a lot of places. The Cambridge team thinks the whole chain holds. Most other astrobiologists think at least one link is weak. That disagreement is what the next chapters are about. Because in April 2025, Madhusudan walked into a press conference and said something that made the argument impossible to ignore. April 16th, 2025. A virtual press conference hosted by the University of Cambridge. Niku Madhusudan, sitting at a desk, with a backdrop of the Hycean world concept art behind him. Reporters from the New York Times, the BBC, Nature, Science, every outlet that covers the cosmos. He began the way scientists begin these things, cautiously. He laid out the 2023 near-infrared data, then the 2025 MIRI data, the statistical strength, 3 sigma. The fact that both DMS and DMDS showed up together, which made the signal harder to explain as noise. The predicted concentrations matching the observed ones. Then came the phrase that broke out of the room. He said that given everything they knew about the planet, the habitable zone orbit, the hydrogen atmosphere, the carbon chemistry, the strength and consistency of the DMS and DMDS signatures, the best explanation for the data was a world with an ocean full of life. He said no known non-biological process produced DMS at the levels they were seeing. In essence, he said it wasn't natural. He also said they weren't claiming to have discovered life. He repeated this several times. The detection needed confirmation, more observations, more independent checks. He called it a revolutionary moment, but he kept trying to stay careful. Careful didn't matter. By the next morning, headlines everywhere said the same thing. Signs of life detected. Alien biology found. Earth is not alone. Most of the stories did include the caveats further down, but the headlines had already done their work. Inside the astronomy community, the reaction was swift and sharp. Stephen Schmidt, an astronomer at Johns Hopkins, said flatly that the evidence wasn't strong. A team at the Max Planck Institute uploaded a preprint within days, arguing the statistical analysis had problems. Harrison Smith, an astrobiologist at the Earth Life Science Institute in Japan, gave interviews questioning whether any gas in any exoplanet atmosphere could ever count as real proof of life. Kevin Stevenson, a researcher at Johns Hopkins University Applied Physics Laboratory, spoke about an overwhelming consensus among his colleagues. The enthusiasm, he said, had outrun the evidence. The criticism wasn't personal. Most of it wasn't even about the data itself at first. It was about presentation. 3 sigma in physics is nowhere near discovery. Particle physics typically requires 5 sigma before a claim is accepted, and even 5 sigma has been wrong before. The muon G-2 anomaly. The 2011 faster-than-light neutrino claim from Opera. Both 3 to 5 sigma results that vanished under scrutiny. Exoplanet atmospheres, where the signal-to-noise ratio is terrible and the systematics are fragile, arguably demand an even higher bar. Madhusudan pushed back. In interviews, he pointed out that his team had laid out the statistics honestly. They hadn't claimed discovery, they had said strongest hints yet, which was technically true. Previous biosignature claims had been weaker than 3 sigma. The problem wasn't the math as presented in the paper. The problem was that the word biosignature had already left the building. The public heard life. The scientists heard overreach. And one scientist in particular, Jake Taylor, was already rerunning the numbers. What he found would unravel the whole statistical case within weeks. Let's talk about what 3 sigma actually means, because the headlines didn't. In statistics, sigma is the standard deviation. It measures how unusual a result is compared to random noise. 1 sigma is pretty common. 2 sigma happens about 5% of the time by chance. 3 sigma is 0.3%, roughly 1 chance in 300 that what you're seeing is a random fluctuation. That sounds solid. It isn't. 3 sigma is the opening bid in physics, not the final word. History has a long list of 3 sigma results that evaporated. In particle physics, there's a standing rule. You need 5 sigma to claim a discovery. 5 sigma means a 1 in 3.5 million chance of being wrong. That rule exists because scientists have been burned again and again by 3 sigma results that felt real and turned out to be noise, bad calibration, or subtle bugs in the analysis. The Higgs boson discovery in 2012, announced at 5 sigma. The faster-than-light neutrino scare from Opera in 2011, a 6 sigma anomaly, which physicists still distrusted, and which turned out to be a loose fiber optic cable. The Bicep 2 gravitational wave claim in 2014, presented with great confidence, retracted within a year when the signal turned out to be dust in our galaxy, not ripples from the Big Bang. 5 sigma isn't even a guarantee. 3 sigma without replication is a research hint, not a result. For exoplanet atmospheres, the problem is worse. The signal itself is tiny. The systematic noise, the imperfections in the telescope, the variability of the star, the assumptions in the data pipeline is often bigger than the thing you're trying to measure. On a quiet, stable system like the Higgs search, you know the noise backward and forward. On a planet transit, you're fighting with a star that flickers, detectors that warm up and cool down, and a model atmosphere that depends on choices you make about what molecules to include. Madhusudan's 3 sigma was for the joint detection of DMS and DMDS. If you looked at DMS alone, or DMDS alone, the confidence dropped. The team's paper acknowledged this, but 3 sigma was the number that went into the press release, and 3 sigma was the number that reporters ran with. Weeks after the announcement, an astronomer named Jake Taylor, based at Oxford, posted a preprint that reanalyzed the same MIRI spectrum. He used a model with only flat opacity, meaning no DMS, no DMDS, just the background absorption of the atmosphere. And he found that this featureless model fit the data nearly as well as the Cambridge team's model, with the biosignature gases in it. That was a problem. Because if a flatline model fits almost as well, it means the bumps the Cambridge team identified might not be real bumps at all. They might just be wiggles in the noise that the more complex model is fitting to. Louis Wellbanks at Arizona State University did his own reanalysis. He found similar issues with the statistical significance. He argued that when the proper corrections for model complexity were applied, the 3 sigma collapsed closer to 1 sigma. At 1 sigma, the result is basically meaningless. You'd expect it from pure noise more than 30% of the time. A full reanalysis was coming. It would be led by NASA. And when it dropped in July 2025, it would speak for the community. There was a second molecule. That's what made the 2025 announcement different from 2023. Not just DMS, but also its cousin, dimethyl disulfide, DMDS. 2 molecules is better than 1. If they both show up together and both are associated with biology on Earth, the probability of it being coincidence drops. That was the Cambridge team's logic, and on the surface, it's sound. DMDS is structurally similar to DMS, same 2 methyl groups. Instead of 1 sulfur atom in the middle, it has 2 sulfur atoms bonded to each other. Formula CH3, 2S2. On Earth, it's produced by the same kinds of marine microbes that produce DMS. Some plants produce it too. Garlic and onions get a lot of their smell from DMDS. When you crush a clove and your eyes water, part of that is DMDS volatilizing into the air. Like DMS, DMDS on Earth is overwhelmingly biological. The natural abiotic sources are minor. If you detect it at parts per million levels in a planetary atmosphere, the same argument applies. Life is the most obvious explanation. Here's the catch. In the MIRI spectrum of K2-18b, DMS and DMDS absorb at overlapping wavelengths. They produce similar-looking bumps in similar places. So the Cambridge team couldn't distinguish cleanly between DMS alone, DMDS alone, or a mixture. Their paper's title was careful about this. New constraints on DMS and DMDS. The and/or was doing heavy lifting. This made the interpretation messier than the headline suggested. Imagine a witness at a trial who says, "I saw a red sedan or a maroon pickup truck. I'm not sure which, but definitely one of them." The claim isn't worthless, but it's not the clean identification the headlines implied. When the critics pushed back, this was one of the first things they focused on. What you have, they said, is a feature in your spectrum at a particular wavelength range. You have two molecule candidates that would fit. You do not have evidence that both are there, which your own analysis acknowledges. There's a deeper issue. At mid-infrared wavelengths, other molecules can produce spectral bumps in the same neighborhood. Methyl chloride, ethane, various sulfur compounds that don't require biology at all. The original analysis didn't include every possible alternative molecule in its models. Critics argued that until you include everything that could plausibly fit, claiming DMS or DMDS specifically is jumping the gun. The Cambridge team's response to this was reasonable. They pointed out that on a hydrogen-rich planet at the temperatures K2-18b is expected to have, the chemistry heavily favors DMS and DMDS over many alternatives. The models predicted them. The wavelengths matched the predictions. Other molecules would require their own explanations for why they were present. The biology story, they argued, was not just possible, but actually the simplest fit. Simpler doesn't mean correct. That's the knife edge the whole debate sits on. The biology hypothesis is elegant. It fits the data. It matches the theoretical predictions the same team made years earlier. All of that is true, but elegance and fit are not proof, especially when the underlying signal is weak and the alternative models aren't fully explored. And behind all of this, there was a bigger question waiting. What if K2-18b isn't actually a Hycean world at all? The Hycean idea was invented in 2021 by the same Cambridge group. Before that, nobody had a name for the kind of world they were describing. The word is a blend, hydrogen plus ocean. A Hycean planet, in their definition, is a sub-Neptune with a hydrogen-rich atmosphere sitting on top of a deep global water ocean. No continents, no ice caps, just air and water, all the way around. The concept did something important for astrobiology. It widened the target list. For decades, the search for habitable worlds focused on Earth twins. Small, rocky, roughly Earth-sized, sitting in the habitable zone of a sun-like star. That's a narrow slice of what's out there. Rocky habitable zone planets around sun-like stars are hard to find and harder to study. Their atmospheres are thin, their transits are shallow. Detecting air on an Earth twin with current telescopes is almost impossible. Hycean worlds change the math. They're bigger, so they have more atmosphere per square mile. Their atmospheres are hydrogen-rich, which puffs them up. A hydrogen atmosphere is much less dense than a nitrogen-oxygen one, so the gas extends higher into space. Deeper air means more absorption during transit. More absorption means an easier detection. If life can survive on these worlds, we can see its fingerprints with the telescopes we already have. That's why K2-18b became the poster child. It fit the profile exactly. The right size, the right temperature range, the right atmospheric composition. The hypothesis depended on one key assumption: that beneath the hydrogen atmosphere, there really was a liquid water ocean. Not supercritical fluid, not ice, water. Pietan Madhusudan's 2020 paper worked out the interior structure. They showed that for a certain range of compositions and temperatures, a sub-Neptune of K2-18b's size and mass could host liquid water at depths of a few tens of miles under a hydrogen layer. The range was narrow. Too much hydrogen, and the pressure at the ocean surface becomes too extreme for liquid water. Too little, and you don't have a thick enough atmosphere to match the observations. The models worked, but they required threading a needle. Here's where other scientists started to push. In 2025, while the DMS debate raged, a separate theoretical paper came out from a different group. They ran more detailed simulations of K2-18b's interior. Their results suggested the planet might have a completely different structure. Not an ocean world at all, but a miscible envelope planet where hydrogen and water are mixed into a single continuous fluid layer. No distinct ocean surface, no liquid-air interface, just a thick, gradient fluid blending from gas at the top to ice at the bottom, with no middle layer where life could easily exist. Another paper proposed that the water and hydrogen in K2-18b's interior had unmixed into layers, but in a configuration that could explain why JWST hadn't definitively detected water vapor in the atmosphere. Again, different from the classic Heightsian picture. The data doesn't pick a winner. All three interior models can be made consistent with the JWST observations, depending on assumptions. What this means is that even if the DMS detection were real, even if the statistics held up, the biological interpretation requires the Heightsian ocean hypothesis to be correct. And that hypothesis is still unproven. The whole tower rests on a flaw nobody has verified. Step back for a second. For most of the modern exoplanet era, sub-Neptunes were considered hostile, not hopeful, hostile. The reasoning was simple. Sub-Neptunes are big. Their atmospheres are thick. If a planet 8 times the mass of Earth formed in the outer part of its solar system and kept a lot of hydrogen during formation, the result is crushing pressure at the surface. Deep down, water would be compressed into exotic phases. Ice 7, ice 10, superionic ice, where oxygen atoms sit in a lattice and hydrogen ions flow through like a liquid. None of it hospitable to biology. The atmosphere at the top is the other problem. Hydrogen and helium, plus methane, ammonia, and other light molecules. No oxygen, no free water at the surface. Temperatures that swing from hundreds of degrees above zero to hundreds below, depending on where in the atmosphere you measure. On paper, sub-Neptunes look like mini versions of Neptune itself. Gas giants in waiting. That picture started to wobble in the late 2010s. Astronomers realized sub-Neptunes are the most common type of planet in the galaxy. Kepler mission data showed that planets roughly the size of K2-18b outnumber Earth-sized ones, at least within the limits of what we can detect. If habitable planets were rare among this most common class of worlds, the math for life in the galaxy got depressing fast. The search for life, most of it concentrated on Earth twins, might be focused on the wrong targets entirely. Some researchers began asking a different question. What if sub-Neptunes aren't all created equal? What if some of them, depending on how they formed and how much hydrogen they held onto, ended up with thin atmospheres over water worlds instead of thick atmospheres over crushed ice? The Cambridge team ran the numbers for K2-18b. What they concluded was that the planet's density, radius, and temperature were all consistent with the Hesian structure. Not definitively proving it, but not ruling it out either. Meanwhile, other groups ran their own models and came to different conclusions. Some arguing the planet was probably a mini Neptune with an atmosphere that went all the way down to a dense, ice-like core. The data can't distinguish between these models yet. All you have from a transit is the planet's radius and a spectrum of its upper atmosphere. What happens below, at the levels where biology would have to live, you can only infer from the thermodynamics. What's not in dispute is that sub-Neptunes will keep mattering. They're common. They're relatively large, so their signals are relatively strong, and if even a small fraction of them turn out to have structures that allow liquid water, they represent the single largest reservoir of potentially habitable real estate in the galaxy. K2-18b is the test case. Whether the answer comes back with biosignatures, with a clear abiotic explanation, or with the most frustrating verdict of all, that the data just can't decide, will shape how humanity searches for life for the next generation of telescopes. Right now, the data is refusing to decide. The JWST spectrum is where the fight happens, line by line, and the lines themselves are stranger than most people realize. Picture the geometry. K2-18 is a red dwarf, small and dim, a quarter the diameter of our Sun. K2-18b orbits it every 33 days. Twice each orbit, from our point of view on Earth, the planet crosses either in front of the star or behind it. The one we care about, the transit, happens when K2-18b passes in front. From our side, that transit lasts a few hours. During those hours, the disk of the planet blocks roughly 1% of the starlight, 1/100th. Tiny but measurable. The transit itself isn't what tells us about the atmosphere. What tells us is the ring. Every planet with an atmosphere has a ring of atmosphere around its silhouette. When the planet is transiting, you're not just looking at an opaque disk. You're looking at an opaque disk with a thin halo of gas around it. Starlight that passes through that halo doesn't get blocked. It gets tinted. Specific wavelengths get absorbed by specific molecules in the halo, and those wavelengths arrive at Earth slightly weaker than they would if the atmosphere weren't there. That's transmission spectroscopy. You compare the star's light during transit to the star's light outside transit, and you subtract. The difference is a spectrum of the planet's atmosphere. Absorption features at certain wavelengths tell you what gases are present. The depth of those features tells you how much. For K2-18b, the atmospheric halo is tiny. The atmosphere is maybe a few hundred miles thick at the levels that matter. Across the planet's disk, that atmospheric ring is an even smaller fraction of the already 1% transit signal. We're talking parts per million of the star's total brightness, changing in specific narrow wavelength bands. The James Webb Space Telescope can measure this, not easily, not cleanly, not without stacking multiple transits and fighting systematic noise at every step, but it can. It's the first telescope that can do this kind of work on planets as small as K2-18b. Here's what shows up in a typical JWST spectrum of K2-18b, a mostly flat line at the level of the planet's blocking effect. Superimposed on that flat line are small bumps and dips, where molecules in the atmosphere are absorbing starlight. A bump at 3.3 microns might be methane. A bump at 4.3 microns might be carbon dioxide. A cluster of bumps between 7 and 10 microns might be DMS or DMDS, or methyl chloride, or water vapor with odd behavior, or artifacts from the instrument itself. All of these are small. The typical amplitude is maybe 50 parts per million of the star's light, meaning the signal is about half the size of a smaller feature on top of an already tiny transit. Reading it requires careful subtraction of the star's baseline spectrum, modeling of the detector's behavior, and assumptions about what molecules to include when fitting the overall curve. Different teams make different choices at every step. That's where the reanalyses come in. And it's also why, when you read that the same data can support either a biosignature interpretation or a flat line, both statements can be simultaneously true. The data is at the edge of what JWST can detect. Tip the analysis one way, and you see a signal. Tip it the other way, and the signal dissolves. The tipping is what the community is arguing about. If you could see the 2025 MIRI spectrum of K2-18b with your own eyes, you'd be underwhelmed. It doesn't look dramatic. It doesn't scream alien biology. It looks like a mostly flat line with some wobbles on top. Those wobbles are the whole story. The spectrum covers wavelengths from about 6 to 12 microns. Along the x-axis, wavelength. Along the y-axis, something called transit depth, the percentage of starlight that's blocked during the transit at each wavelength. On a perfectly flat, featureless atmosphere, that curve would be a horizontal line. Any deviation from horizontal is an absorption feature, where a molecule is eating light. The Cambridge team identified two main features in the MIRI spectrum: a bump in the range of 9 to 10 microns, which they attributed to DMS absorption. A second, partially overlapping bump in the 7 to 8 micron range, which they attributed primarily to DMDS. Both features showed up at heights above the baseline that, under their statistical model, exceeded the noise threshold at 3 sigma combined confidence. When Jake Taylor's reanalysis came out, here's what it did. He took the same raw data, ran it through a different pipeline, and fit it with the simpler model. Just a flat opacity baseline, no biosignature molecules at all. He asked a straightforward question. How much worse does the flat model fit the data compared to the Cambridge model with DMS and DMDS? The answer was, not much worse. In statistical terms, the flat model had comparable likelihood to the biosignature model. That doesn't mean the bumps don't exist. It means the bumps aren't statistically required. You can draw a line through the data without them that's almost as good as drawing a line with them. When a signal and a null hypothesis both fit the data, you don't have a detection. You have a preference. The Cambridge team prefers the biosignature interpretation because it matches their theoretical predictions and their Hessian framework. The critics prefer the flat interpretation because it's simpler and doesn't require invoking molecules that are hard to justify. In August 2025, an even more thorough reanalysis appeared. Published in Astronomy and Astrophysics, led by researchers doing a joint analysis of all three JWST instrument datasets on K2-18b, NIRISS, NIRSPEC, and MIRI. Rather than looking at one instrument in isolation, they combined everything. When they did, they concluded that the evidence for DMS and DMDS was insufficient. The features that showed up in MIRI didn't line up cleanly with what should appear in the near-infrared instruments if the molecules were really present at the claimed concentrations. The team's response essentially was that different pipelines make different assumptions, and their original analysis remained defensible within its own framework. The debate didn't get resolved, it got more technical. The arguments moved from press conferences into footnotes about retrieval methods, prior distributions, and pipeline calibration choices that almost nobody outside the field can evaluate. This is what a real scientific controversy looks like. Not cinematic, not clean. A slow grind of dueling preprints, each one adjusting a parameter, each one shifting the conclusion a little. The truth is sitting inside a spectrum that's right at the edge of what our best telescope can measure. There was still one more problem looming. The planet next door, in astronomical terms, had done this dance before. Within a week of the April 2025 announcement, the preprint server at R-Archive, where astronomers post papers before formal publication, started filling up with responses, most of them skeptical. The first came from a team at the Max Planck Institute for Astronomy in Germany. They questioned the statistical significance reported in the Cambridge paper. Specifically, they argued that the retrieval method used to estimate the DMS signal had parameters that weren't properly constrained, meaning the 3 sigma number might be inflated. When they redid the analysis with tighter constraints, the significance dropped substantially. Then came Jake Taylor's paper from Oxford, then Luis Wellbanks's analysis from Arizona State. Each one found different issues, but they converged on the same general conclusion. The signal is weaker than the headline number suggests. Reasonable alternative analyses make it vanish. The critics weren't saying the Cambridge team was wrong on purpose. Nobody was accusing anyone of fraud. The issue was subtler and, in a way, more uncomfortable. The question was whether, given the state of JWST data on small exoplanets, any biosignature claim could be made responsibly at the level of certainty the public was hearing. Harrison Smith at the Earth Life Science Institute in Japan gave a series of interviews that summarized the concern. JWST, he pointed out, is a telescope. It measures gases in atmospheres. It is not a life detector. The leap from "we measured a gas" to "this gas is evidence of biology" requires ruling out all non-biological sources. For DMS, we can't do that yet. The chemistry of hydrogen-rich atmospheres under red dwarf radiation is not fully characterized. Abiotic DMS production pathways haven't been fully mapped. Smith's co-author, Cole Mathis at Arizona State, put it more bluntly in a 2023 essay he and Smith had written together. Ruling out false positives for exoplanet biosignatures, they argued, might be fundamentally harder than ruling them in. At least on Venus, Earth's twin, we could send probes, do follow-up measurements, argue in detail. On a planet 124 light years away, we're stuck with whatever the telescope tells us. We can't taste the ocean. We can't scoop up a sample. The signal is the evidence, and the signal is ambiguous. Kevin Stevenson at Johns Hopkins University Applied Physics Laboratory was direct. The overwhelming consensus in the exoplanet community, he said, was that the enthusiasm had outrun the evidence. He used a phrase that stung, the boy who cried wolf. Nobody wanted a series of false detection claims to damage public trust in science. If biosignatures kept getting announced and then kept getting retracted, By the time a real one came along, nobody would believe it. This wasn't just about one paper, it was about the credibility of the entire field. Exoplanet atmosphere research has spent decades building up to this moment. The James Webb Space Telescope cost $10 billion and took 25 years to launch. If the first potential biosignature detection it produces turns out to be noise, and if that noise was oversold to the public, the reputational damage to astrobiology could be severe. The Cambridge team saw it differently. They argued they'd been careful in the paper. They had said, strongest hints, not discovery. The distortion was in the media coverage, not in the science. Press releases are interpreted by journalists, and journalists need hooks. The journals, though, don't run on press releases. They run on replication. Each of the critics had a specific angle. It's worth knowing what each of them actually argued, because the debate isn't one big fight. It's half a dozen smaller fights, all happening at once. Jake Taylor, at Oxford. His analysis focused on what's called model selection. When you fit a spectrum, you need to compare multiple possible models. A flat, featureless baseline, a model with DMS, a model with DMDS, a model with both, a model with other molecules. Each additional molecule adds parameters, and more parameters give you more flexibility to fit random wiggles as if they were signals. Taylor showed that when you penalize the more complex models for having more parameters, a standard statistical practice called the Bayesian information criterion, the biosignature model's advantage over the flat model shrinks dramatically. Without that penalty, 3 sigma. With it, much less. Luis Wellbanks, at Arizona State. His analysis centered on the retrieval process itself. When astronomers extract molecular abundances from spectra, they use a method called atmospheric retrieval. You start with a prior guess about what's in the atmosphere, and you let the algorithm adjust until the model matches the data. The priors matter. If your prior assumes DMS is likely to be present, the algorithm will find DMS. If your prior is agnostic, DMS becomes harder to pin down. Wellbanks argued that the Cambridge team's priors may have been too narrowly focused. The Max Planck team, their paper compared the MIRI data to the previous NIR spec data from the same planet. If DMS is really in the atmosphere at the claimed concentrations, it should show up in both wavelength ranges. They found that the near-infrared spectrum didn't line up with what you'd expect given the mid-infrared claim. That inconsistency, they argued, was a red flag. The Astronomy and Astrophysics Joint Analysis in August 2025. This one combined all 3 JWST instrument datasets, NIRISS, NIRSPEC, and MIRI. Their conclusion was bluntest. The combined evidence for DMS and DMDS was insufficient to support a detection. They also explored alternative molecules that could produce similar spectral features, including methyl chloride, and concluded that the data couldn't distinguish between several plausible options. Then came the big one. July 2025, NASA JPL, Renyuhu leading. This was the reanalysis with the most weight behind it. Not because Hu is more prominent than the other critics, but because of 2 things. First, the paper involved NASA as an institution, which carries institutional credibility separate from any individual author. Second, and more striking, Madhusudan himself was listed as a co-author. The Cambridge team had worked jointly with the NASA team on the reanalysis. This wasn't an outside group attacking. This was the original group participating in a collaborative, independent review. The WHO paper's conclusion was measured but clear. The atmosphere of K2-18b is complex and water-rich, confirming many previous findings, but the evidence for DMS specifically, on closer examination with more rigorous techniques, is not conclusive. The July 2025 paper didn't say the signal was fake. It said the signal wasn't strong enough to justify the biosignature interpretation yet. For most of the community, that was the end of the discussion for now. The claim hadn't been debunked, it had been downgraded. From strongest hints yet back to interesting possibility requiring more data. Madhusudan did something that a lot of researchers wouldn't. He signed onto the reanalysis. There's a specific version of the K2-18b argument that captures the whole thing in a single image. It's called the flatline problem, and once you see it, you can't unsee it. Pull up the MIRI spectrum in your head. Wavelength on the bottom, transit depth on the side. Across the range from 6 to 12 microns, you have a set of data points, each one an average measurement at a specific wavelength, with an error bar sticking up and down. Now ask a simple question. Can you draw a horizontal line through this data? Not a fancy curve. Not a model with molecular features. Just a straight horizontal line. The answer is yes. You can. If you pick the right height for the line, it passes through most of the data points within their error bars. It's not a perfect fit, but it's not a bad one either. Statistically, it's what's called a plausible model. Now draw a model with DMS and DMDS included. This model has bumps at the wavelengths where those molecules absorb. It's also a plausible fit to the data. Which model is right? That's the whole fight. Both fit. Neither fit is perfect. The more complex model with biosignature molecules captures slightly more of the structure in the data. The simpler flat model is, well, simpler. There's a principle in science called Occam's razor. Don't multiply entities beyond necessity. If two models fit the data equally well, prefer the simpler one. Applied here, the razor tilts toward the flat line. No biosignature molecules required to explain the spectrum. Therefore, don't invoke them. The Cambridge team's counter is that the flat line doesn't fit quite as well. The DMS-DMDS model fits better by a measurable amount. The improvement isn't huge, but it's statistically favored according to their analysis. The problem is that measurable amount depends on how you measure it. Every statistical test carries assumptions. Every pipeline carries choices. Subtle differences in how you treat instrument systematics, how you handle data gaps, how you model the star's variability, all of these can nudge the balance between flat model wins and biosignature model wins. If the planet's atmosphere were richer, the argument would be easier. If instead of 3 sigma bump, we had a 10 sigma mountain, there'd be no debate. A clear spectral feature at a biosignature wavelength, standing proud above the noise, would settle things. Every team would see it. Every pipeline would return it. We don't have that. We have the edge of what JWST can measure, exactly where statistical subtleties dominate. There's a lesson here about where we are in the search for life. We are so close to being able to answer the question that we can feel it. JWST represents the first telescope in human history powerful enough to even attempt this measurement on a habitable zone planet. That's extraordinary. It also means we're going to spend years on the edge of detection, arguing about what the edge shows. K2-18b probably won't give up a clean answer from JWST alone. The signal is right at the margin and staying there. For a real answer, you need something bigger. A telescope that can take the flat line and turn it into a clear spectrum, full of features so obvious no analysis trick can erase them. Those telescopes are coming, but the K2-18b debate was about to run into its most important historical parallel. A planet next door, Venus, that had already walked this same path 5 years earlier, July 16th, 2025. A preprint appeared on AirQuill with a long list of authors. At the top, Renyu Hu of NASA's Jet Propulsion Laboratory. Further down the list, Niku Madhusudan, the original Cambridge team leader, listed as a collaborator on a paper that would, in effect, pull the brakes on his own April announcement. The paper's title was Direct. It described a joint analysis of JWST transmission spectra for K2-18b, combining data from multiple instruments and reassessing the chemical interpretation. No press conference, no virtual backdrop of a Hycean world. A preprint, quietly posted, with the kind of sober language that scientific papers use when they're trying not to make waves. The waves came anyway. Renyu Hu is a senior research scientist at JPL, one of the most respected exoplanet atmosphere modelers in the field. He has worked on Venus, on Mars, on atmospheric chemistry of rocky planets, and on photochemistry in hydrogen-rich environments. When he signs onto a paper saying the evidence for DMS is inconclusive, the community listens. The reanalysis did several things at once. It reprocessed the raw JWST data with a different pipeline. It applied more conservative statistical treatment. It expanded the set of molecules considered as alternatives to DMS and DMDS, including nitrogen compounds and halogenated species that could produce similar mid-infrared features. And it looked specifically at consistency between the near-infrared and mid-infrared observations. The conclusions were careful. The atmosphere of K2-18b is rich in water vapor, consistent with earlier observations. The overall picture of a hydrogen-rich envelope with carbon chemistry remains solid. The claim that either DMS or DMDS has been detected at a level justifying the label biosignature, however, does not survive the more rigorous treatment. The data is consistent with several alternative explanations, including no DMS at all. The 3 sigma number reported in April under the joint analysis shrinks to something closer to 1 to 1.5 sigma, depending on the assumptions. For the public, that translation is simple. The signal got weaker. The biosignature claim got retracted, in all but name. For Madhusudan, signing onto the paper was a specific act. He could have refused. He could have stood by the April results and let the debate continue at a distance. Instead, he participated in the reanalysis, contributed to the methodology, and attached his name to a conclusion less dramatic than the one he had championed 3 months earlier. Whatever else one might say, it was a scientifically honorable move. In follow-up interviews, Madhusudan didn't abandon the biosignature hypothesis. He said the detection hadn't been ruled out. He said more data was needed. He pointed to additional JWST observations already approved, which would extend the spectrum with more transits and more wavelengths. If the signal was real, those observations would strengthen it. If it wasn't, they would drive it further down. The broader community treated the WHO paper as the field's official response. The April excitement faded from headlines. The story shifted from possible signs of life to claim fails to replicate, though most coverage was more charitable than that. The truth was somewhere in between. The claim hadn't been disproved. It just hadn't been confirmed. The lesson this was teaching astrobiology wasn't new. The field had been through this before, on a planet much, much closer to home. In September 2020, 5 years before Madhusudan's April announcement, another team had stood in front of another press conference and made a similar claim. Phosphine, a gas produced on Earth almost exclusively by biology or by industrial processes, had been detected in the clouds of Venus. Venus, our nearest planetary neighbor, the second rock from the Sun. A world of sulfuric acid clouds and surface temperatures hot enough to melt lead. Nobody had seriously proposed life on Venus in decades. The idea was fringe, at best. Then the phosphine paper landed in Nature, and suddenly Venus was a biosignature candidate. The detection came from a team led by Jane Greaves at Cardiff University. They used 2 ground-based telescopes, the James Clark Maxwell Telescope in Hawaii and the ALMA Array in Chile. They saw a spectral absorption feature at a wavelength consistent with phosphine. The concentration they inferred was around 20 parts per billion. Low, but far higher than any known non-biological process on Venus could produce. The reaction mirrored what would happen to K2-18b 5 years later. Excitement in the press, skepticism from other astronomers, reanalyses of the data, starting almost immediately. Teams using different pipelines, different noise models, different baseline subtractions. Some found the phosphine signal survived, others found it vanished entirely. The ALMA data had calibration issues that hadn't been fully accounted for in the original paper. When corrected, the signal weakened. Other teams pointed out that a sulfur dioxide feature at a nearby wavelength could mimic phosphine's fingerprint under certain analysis choices. And sulfur dioxide on Venus is abundant and completely expected from volcanic and atmospheric chemistry, with no biology required. 5 years later, the Venus phosphine claim is still unresolved, not definitively refuted, not definitively confirmed. Some Greaves follow-up observations suggest the signal is variable, appearing and disappearing on timescales of months. Other researchers argue that's just noise. Whatever the truth, the dispute has gone on for half a decade, and there's no clean answer in sight. Everything about Venus is easier than K2-18b. Venus is next door. We can send spacecraft. We have 50 years of probe data on its atmospheric chemistry. We know the pressure, temperature, and composition at every altitude in detail. If any biosignature claim in the solar system should be resolvable, it's one on a planet we've been studying for generations, and we can't resolve it. On K2-18b, we have none of those advantages. No probes, no direct sampling, no way to do follow-up observations beyond more of the same type. More JWST transits, more spectra, more statistical retrievals. The tools we have to check ourselves are the same tools that produce the ambiguous signal in the first place. The Venus lesson is humbling. If we can't resolve biosignature claims on a planet we can touch, how will we resolve them on a world 124 light years away? The answer is, maybe we can't. Maybe biosignatures on exoplanets will always carry this kind of ambiguity. Maybe the best we can do from here is to catalog suggestive signals without being able to verify any of them conclusively. That's a hard pill for the field to swallow, and some astrobiologists are starting to say it out loud. Not everyone is sanguine. Sarah Rugheimer at York University, an atmosphere modeler, has said she would still open a bottle of champagne if we found oxygen, methane, water, and carbon dioxide together on an exoplanet. She thinks the right combination of gases could be compelling. Others disagree. The skeptics aren't saying we'll never find life. They're saying that atmospheric gases alone, filtered through starlight across light years, might not be enough, ever. The whole case for K2-18b biology depends on one claim: that no known non-biological process produces DMS at the observed levels. If that claim is false, if abiotic pathways exist that can make DMS in significant quantities under K2-18b conditions, then the biosignature argument collapses, even if the detection itself turns out to be real. Critics have been poking at this claim since the day the April paper came out. The first and most obvious counterexample is photochemistry. DMS contains a sulfur atom and 2 methyl groups. The building blocks are hydrogen, carbon, and sulfur. All 3 are common in hydrogen-rich planetary atmospheres. Under the ultraviolet radiation pouring out of a young red dwarf, complex sulfur chemistry can happen in unexpected ways. A team, including researchers at the University of California, Irvine, and others modeled K2-18b's atmosphere with a detailed photochemical network, accounting for the specific ultraviolet spectrum of K2-18's radiation. Their results suggested that under certain atmospheric compositions and temperatures, DMS could be produced photochemically at concentrations approaching parts per million. Not guaranteed, not necessarily the right answer for K2-18b, but plausible enough to undermine the only biology can do this argument. The more the chemistry gets explored, the weaker that argument becomes. Hydrogen sulfide, sulfur dioxide, carbonyl sulfide, and various methyl sulfur compounds are all involved in a chemical web that can, in principle, produce DMS without any biology. The web isn't well characterized yet. We don't have lab experiments simulating the exact radiation environment and pressure of K2-18b's upper atmosphere, producing the exact chemistry that would occur there. We have models, and the models disagree. That disagreement is a problem. It means the confident statement, no known non-biological process produces DMS at these levels, is technically a statement about our incomplete understanding, not about nature. We might just not know yet. Separately, some chemists have started arguing that the whole framing of DMS as biogenic on Earth is oversimplified. A small fraction of atmospheric DMS on our planet does come from non-biological sources. Volcanic outgassing produces trace amounts. Certain mineral interactions in hydrothermal systems can generate it. On Earth, these sources are dwarfed by biology, but that dominance depends on Earth-specific conditions. A planet with different geology, different ocean chemistry, or different atmospheric composition might have very different ratios. There's also the mixing problem. Even if DMS is produced somewhere on K2-18b, whether by life or not, getting it to detectable levels in the upper atmosphere requires vertical mixing strong enough to transport it from wherever it's made to where JWST can see it. The atmospheric dynamics of tidally locked sub-Neptunes are not fully understood. The mixing could be strong, allowing biosignature gases to accumulate high up, or it could be weak, keeping them trapped below. The Cambridge team ran these numbers and argued that the mixing is sufficient. Critics argue the numbers could go either way. This is what it looks like when a field is at the frontier. Every assumption is contested because no one has the ground truth. None of this proves K2-18b doesn't have life. It proves that the argument from DMS alone, without other supporting evidence, can't carry the weight the headlines placed on it. If DMS is there, it might be biology. It might also be photochemistry in an atmosphere we haven't yet modeled correctly. The data we have can't distinguish. And shortly after the April announcement, a discovery somewhere far from K2-18b made the abiotic DMS question even messier. In 2024, a team of researchers analyzing samples from comet 67P/Churyumov-Gerasimenko published something that caught astrobiologists by surprise. The European Space Agency's Rosetta mission had flown alongside this comet for 2 years, sampling its gas and dust with instruments designed to identify the molecules present. Deep in the archived data, the team found DMS, not a trace, not ambiguous. A clear, measurable abundance of dimethyl sulfide in the coma of a comet that formed in the outer solar system and has been in space essentially forever. That changed the conversation. Comets are fossils. They're chunks of the primordial solar system, preserved in deep cold, carrying with them the organic chemistry that existed before Earth formed. They're thought to be one of the main delivery mechanisms that seeded the young Earth with water and organic molecules. They have never been alive. They have never hosted life. Whatever chemistry happens on a comet, it happens without biology. Finding DMS on a comet meant that at least some of the DMS in the universe is abiotic, produced by non-living chemistry in the cold of space. The molecules can form in protoplanetary disks, survive in icy bodies, and persist for billions of years. Then came a follow-up discovery, published in 2025. Astronomers using radio telescopes detected DMS in the interstellar medium, the gas and dust between stars, the raw material from which new stars and planets form. The detection was in a specific cloud where other complex organic molecules had already been mapped. DMS, it turned out, was just one more member of a growing catalogue of organic chemistry that happens in space without any biology anywhere nearby. For the K2-18b argument, these detections were bad news. The Cambridge team's core claim had been that DMS is a biological molecule. On Earth, that's true in the sense that almost all of Earth's DMS comes from life. But across the wider universe, DMS turns out to be something else. It's a fairly common molecule that shows up wherever the right carbon-sulfur-hydrogen chemistry exists, whether or not anything is alive. This doesn't kill the K2-18 BE biosignature hypothesis. DMS on a comet or in an interstellar cloud is at very low concentrations, and it's being produced by cold cosmic chemistry over long timescales. K2-18b's observed DMS, if real, would be at parts per million in a warm atmosphere, orders of magnitude higher. There's a difference between DMS exists abiotically somewhere and DMS at high concentrations in a habitable zone planet's atmosphere is abiotic. Still, the existence of even low-level natural DMS production undercuts the simplicity of the biosignature argument. You can no longer say, there's no other way. You can only say, biology is one way, and other ways we know about don't produce enough to explain the observed signal. That's a weaker statement, and it depends on the accuracy of the abiotic models. Sarah Rugheimer at York University, who has worked on biosignatures for years, has been actively exploring abiotic pathways for the classic biosignature gas combinations. She's not trying to rule out life. She's trying to establish what non-biological chemistry can and can't do, so that when a real biosignature shows up, we can recognize it against a known background. That work is ongoing. For K2-18b, it's not finished. The background chemistry is still being mapped. The search for alien life, it turns out, is partly a search for what alien chemistry can look like without life at all. Until we know that space thoroughly, we can't know when we've stepped outside it. What does the light from a red dwarf do to a hydrogen atmosphere? That question sounds narrow. It matters enormously. Red dwarfs emit most of their light in the infrared. Their ultraviolet output is weaker than the sun's in absolute terms, but relative to their visible light, it's often stronger. They also flare often, pulsing bursts of high-energy radiation that are brief but intense. Over billions of years, a planet in the habitable zone of a red dwarf gets hit with a cumulative dose of UV that's different in character from what Earth receives from our sun. On a hydrogen atmosphere with sulfur compounds, that radiation drives chemistry. Energy breaks bonds. Hydrogen sulfide becomes H and SH fragments. Methane breaks into CH3 radicals. These fragments can recombine into larger molecules. DMS is one possible recombination product. So are a dozen other sulfur-carbon-hydrogen combinations, some of them short-lived, some stable for years in the right conditions. Models of this photochemistry have been run by multiple groups. The answers depend on inputs that aren't well known. How much UV does K2-18 actually emit? We have measurements, but they're limited. What are the abundances of the parent molecules at different altitudes? We don't know for sure. What's the temperature profile in the upper atmosphere? We have estimates with wide error bars. Some models, with certain assumptions, produce DMS at concentrations approaching what JWST reports. Other models, with different assumptions, produce essentially none. The spread in predictions is wider than the signal itself. A team led by Shangmin Tsai at UC Riverside and collaborators ran detailed photochemical simulations of K2-18b's atmosphere, including sulfur chemistry under the specific radiation of its host star. Their results showed that the atmospheric DMS abundance depends sensitively on the deep atmosphere sulfur inventory, the vertical mixing, and the UV flux. Under some plausible combinations, DMS could be produced photochemically at detectable levels. Under others, it couldn't. This is typical of frontier science. The question, can photochemistry alone explain the K2-18b signal, doesn't have a clean yes or no. It has a range of possibilities, depending on parameters we haven't measured directly. There's a broader implication here. If photochemistry can produce DMS in hydrogen-rich atmospheres around red dwarfs, then DMS is no longer a reliable biosignature for this class of planet, which is a significant problem, because a large fraction of the potentially habitable planets we can currently observe orbit red dwarfs. Proxima b, TRAPPIST-1's planets, Ross 128, b, and K2-18b itself. If the targets we can study best are also the targets where biosignatures become ambiguous, The search for life has to shift strategy. Different molecules, different combinations, or different planets around different kinds of stars, even though those are harder to observe. Some researchers have proposed that the real test for life has to come from combinations of gases that are harder to fake. Oxygen and methane together, for instance, on a planet in radiative equilibrium with its star. Those two molecules react with each other and disappear unless something keeps replenishing them. On Earth, that something is biology. On other worlds, it could in theory be abiotic, but the pathways are more constrained. For K2-18b, the DMS and DMDS combination was supposed to be that kind of test. Two biogenic molecules, present together, hard to explain abiotically. The abiotic chemistry community, over the course of 2025, kept finding ways to produce at least one of them without biology. The second detection didn't firm up the case as much as the Cambridge team had hoped. Meanwhile, another aspect of K2-18b was itself becoming a wildcard. 33 days per orbit. Close enough to its star that the planet's rotation has frozen long ago. One side always faces the star. The other side always faces the night. This is tidal locking, the same physics that keeps one face of the moon permanently turned toward Earth. On K2-18b, that geometry controls the weather. Climate models of tidally locked planets are their own subfield of science. They have been running simulations of Proxima b, TRAPPIST-1's habitable worlds, and K2-18b for years. The picture that emerges is strange and specific. On the day side, where the red sun hangs forever, heat piles up. Atmosphere expands. Water, if any exists, evaporates. On the night side, cold air sinks and freezes. The temperature gradient between the two sides creates the most intense, sustained winds in planetary science. In some models, wind speeds on tidally locked sub-Neptunes exceed 1,000 miles per hour at the boundary between day and night. Those winds carry everything with them: water vapor, methane, and in the case of K2-18b, whatever DMS is in the atmosphere. The global circulation smears chemistry across the planet, mixing day-side photochemistry with night-side cooling. Hot regions with cold, upper atmosphere with lower. A 2024 climate model of K2-18b suggested the planet has a jet stream system unlike anything on Earth. A prograde flow in the direction of the planet's rotation in the lower troposphere. A retrograde flow going the opposite way higher up. In between, a layer of turbulent mixing where the two rivers of air collide. For a molecule like DMS, the altitude at which it exists matters hugely. High up, it can be seen by JWST. Low down, it's invisible. The mixing determines whether a DMS signal even reaches the part of the atmosphere we observe. This matters for interpretation. Even if biology produces DMS in K2-18b's hypothetical ocean, getting it to the altitudes JWST probes requires the right kind of atmospheric dynamics. If the models are wrong about the mixing, the observed concentration could be either higher or lower than what you'd predict from the ocean source alone. The winds also create geographic variation. Transit spectroscopy averages over the whole terminator. The ring of atmosphere at the boundary between day and night that we see during a transit. If DMS is concentrated on one side of the planet and absent on the other, the average we measure is some combination of both, which depends on where the planet is in its orbit when we observe it. The Cambridge team's spectrum represents this average view. Critics have argued that a more detailed model of atmospheric circulation is needed before any abundance can be claimed reliably. Without a three-dimensional picture of where the molecules actually are, a single number like 10 parts per million DMS is a blunt summary of what might be a very spatially complex reality. Tidal locking also does something to the tops of tidally locked planets that's specific to sub-Neptunes. The very upper atmosphere, exposed to the star's radiation, heats up and expands. Some of it escapes into space. Over billions of years, this escape can strip away significant mass. K2-18b has held onto its atmosphere so far, which tells us something about its gravity and its formation. But the atmosphere it has today is not the atmosphere it started with. The DMS we're looking for, if it's there, exists in an envelope that's been shaped by billions of years of atmospheric erosion and reformation. Everything about K2-18b is in motion. The winds, the chemistry, the atmospheric escape. A snapshot from JWST captures one moment in a process that never stops. If the ocean beneath this atmosphere even exists, here's a question most coverage has glossed over. Does K2-18b actually have a liquid water ocean? The Hiceian hypothesis assumes yes. The biological interpretation of DMS requires yes. Everything downstream in the story, the microbial bloom pumping sulfur into the sky, the habitable zone real estate, the Hiceian category itself, rests on there being an actual ocean at some depth inside K2-18b with actual liquid water in contact with actual atmosphere. The evidence for that ocean is indirect and contested. What JWST measures is the atmosphere. From there, astronomers infer what the interior must be like. Given the planet's mass, radius, and observed gas abundances, multiple interior structures can match the same external observations. One model, the one Madhusudan and colleagues have championed, places a hydrogen-rich atmosphere on top of a liquid water ocean, on top of a rocky or icy core. The ocean provides the habitability. The model works if the planet's water content is at a specific fraction of its total mass, roughly between a few percent and a few tens of percent. A competing model, published in 2024 by a group not affiliated with the Cambridge team, argues that the planet is better fit by a miscible envelope. In that picture, hydrogen and water are not separated into distinct atmospheric and oceanic layers. Instead, they're mixed together in a continuous fluid that transitions smoothly from gaseous at the top to supercritical in the middle to icy at the bottom. No distinct ocean surface, no clean boundary where biology could take hold on a seafloor or in a sun-dappled surface layer. A third model, proposed in 2025, suggests the water and hydrogen in K2-18b's interior may have unmixed into layers in a way that differs from the classic Hiceian picture. In this version, the atmosphere might be mostly dry at the levels we observe, with water trapped in a deeper layer inaccessible to JWST. That model attempts to explain why JWST has had difficulty definitively detecting water vapor in the upper atmosphere, something that would be expected if the classic Hiceian ocean existed. These three interior models predict different chemistry, different habitability, and different biosignature expectations. The data from transit spectra could be fit by all of them, depending on what assumptions you make. There's no observation currently available that decisively picks one. This is a structural problem for the biosignature claim. The DMS interpretation doesn't just require that DMS is really in the atmosphere. It requires that there's a biologically productive ocean producing it. If the planet is a miscible envelope world with no ocean, biology as we understand it doesn't have anywhere to live. If the unmixed interior model is right, the habitable layer might be too deep or too exotic to support microbes. The Cambridge team has emphasized that the Hycean structure remains consistent with the data. Their critics emphasize that inconsistency with the data hasn't been demonstrated for the alternative structures either. Everyone agrees that the interior structure of sub-Neptunes is one of the most important unsolved questions in exoplanet science. The tools to resolve it are still being built. What would resolve it? Potentially, better measurements of the planet's mass and radius with greater precision, observations of its tidal response through future gravitational wave or astrometric missions, detailed atmospheric retrievals across more wavelengths. None of this is imminent for K2-18b specifically. So the ocean is a hypothesis, a reasonable one, backed by careful modeling, but not yet confirmed. The biosignature claim is a hypothesis on top of a hypothesis. Even if the signal and the spectrum were rock solid, and it isn't, you would still need the ocean to exist and to be biologically productive before you could call it evidence of life. Nested uncertainties, each one small, each one plausible. Stacked together, they leave a lot of space between intriguing observation and we found aliens. 10 parts per million. That's the rough concentration of DMS in K2-18b's atmosphere, according to the April 2025 Cambridge paper. For context, Earth's atmospheric DMS concentration sits around 1 part per trillion, which is 10,000 times lower. Think about what 10 parts per million means. Imagine a balloon filled with the air of K2-18b. If you could sort every molecule in that balloon by type, 10 out of every million would be DMS. The rest would be overwhelmingly hydrogen with traces of methane, carbon dioxide, water vapor, and everything else. On Earth, DMS at 10 parts per million would be an overwhelming smell. Our olfactory system can detect DMS at parts per trillion. 1,000,000 times that would be unbearable. If you stood on K2-18b's surface, assuming you could survive, you would be immersed in a smell that would dominate everything else. A sharp, organic, sulfur-edged scent, thick enough to taste. For biology to produce and sustain DMS at this level, a lot of metabolism has to be happening. On Earth, the global ocean output is around 20 to 30 million tons per year, and even that only sustains parts per trillion atmospheric concentrations, because the oxygen-rich atmosphere destroys DMS within a day or two. Atmospheric photochemistry keeps pulling DMS out of the air, which is why Earth's steady-state concentration stays so low. On K2-18b, with a hydrogen atmosphere, the photochemistry is different. DMS doesn't get destroyed as quickly. Some models suggest it could persist for a year or more before breaking down. Longer lifetimes mean higher steady-state concentrations from the same production rate. So 10 parts per million on K2-18b doesn't necessarily require 10 million times Earth's biological output. It might require something more like 1,000 times Earth's output, spread over a larger atmosphere with slower chemistry. 1,000 times Earth's biological DMS output is still an enormous amount. To generate it, you need an ocean teeming with something analogous to phytoplankton, pumping sulfur compounds into the air at a furious rate. Not a quiet biosphere at the edge of survival. A roaring one. Madhusudan's team has emphasized this as a feature, not a bug. Their models of Hycean worlds predict that microbial biospheres, if they exist, could be extremely productive. The hydrogen atmosphere, combined with the warm ocean and the specific chemistry of a Hycean world, could support biological throughput far exceeding Earth's. The 10 parts per million figure is, in their view, what a thriving alien biosphere would produce. A feature of the model, predicted before the observation. Critics note that thriving alien biosphere is a lot of biology to assume for one spectral bump. If the signal turns out to be only a few parts per million instead of 10, the biological model still works. But the constraints tighten. Below a certain concentration, abiotic chemistry becomes a real competitor. Above a certain concentration, the biomass required becomes implausible given the available energy in the ocean. The current data doesn't pin down the concentration precisely. The 10 parts per million figure has error bars. The actual abundance could be meaningfully higher or lower. Until more data comes in, the estimate itself is a working number with room to move. Precision matters here because the entire interpretation hinges on quantitative details. A few parts per million is one kind of story. Tens of parts per million is another. Parts per billion would be a third, and much weaker case. JWST can only do so much. Future telescopes may need to do the rest. And before we build those telescopes, there's a question worth asking. How much life does it actually take to produce a detectable biosignature? Suppose K2-18b has biology. How much of it? What kind of biosphere would be required to explain a 10 parts per million DMS signature at 124 light-years distance? This is a real calculation, and it's been done by several groups. On Earth, the marine phytoplankton that produce most of our DMS are distributed in the upper layer of the ocean, roughly the top 300 feet, where sunlight still penetrates enough for photosynthesis. Their total biomass is estimated at a few gigatons of carbon. Their DMS output, as noted, is tens of millions of tons per year. For K2-18b, the numbers have to scale. Hycean worlds are larger. Their oceans, if they exist, could be tens of miles deep. The relevant question is whether biology on K2-18b would need to be more productive per unit volume than Earth's, or simply spread over a larger volume at Earth-like productivity. Several papers have tackled this. A 2024 analysis argued that if Hycean life has Earth-like per-cell DMS production rates, the required ocean biomass on K2-18b might be comparable to Earth's in order to produce the observed signal, given the thicker atmosphere and slower photochemical destruction. That's remarkable. It means the detection, if real, doesn't require a biosphere orders of magnitude larger than our own. It requires one comparable to Earth's, or at most a few times larger. Manageable, reasonable. Within the realm of what we know life can do if we grant that life exists there at all. But the calculation depends on assumptions. What if Hycean microbes are less productive than Earth's phytoplankton? Then you need more of them. What if they produce more DMS per cell? Then you need fewer. Nobody knows the actual biology. Nobody has even a theoretical framework for hydrogen ocean world metabolism, that's been validated against anything. There's a deeper issue. Terrestrial phytoplankton produce DMS from DMSP, and DMSP is synthesized from sulfur compounds they pick up from the ocean. That sulfur comes from continental weathering, from hydrothermal vents, from cycling with the atmosphere. A Hycean world has no continents. Its sulfur budget depends entirely on what's in the ocean and what exchanges with the atmosphere. If the ocean is sulfur poor, even a thriving biosphere couldn't generate much DMS. Is K2-18b's hypothetical ocean sulfur rich? We don't know. Its atmosphere does contain some sulfur compounds, which suggests some availability, but the total inventory is anybody's guess. The chemistry of a hydrogen water world with a rocky core under a red dwarf's radiation has no good Earth analogue. We're extrapolating into unknown territory, and the extrapolation determines the answer. The bottom line is that the biomass problem isn't a killer for the biological interpretation, but it's not a slam dunk either. The numbers work out at roughly Earth-scale biology under optimistic assumptions. Under pessimistic ones, you need either a much larger biosphere or some unknown mechanism to amplify the DMS signal. Neither case is absurd, and neither is confirmed. Exoplanet astrobiology has become, in a specific sense, a probability game. Every link in the chain, detection, interior, habitability, biology, atmospheric transport, carries a probability of being right. You multiply them together to get a joint probability that the biosignature interpretation is correct. When each individual link is 50 to 70% likely, the combined probability for a 6-link chain drops into the single digits. That doesn't mean biology is ruled out. It means the confidence statement "we detected signs of life" is not justified by the current evidence, even under the most generous interpretation. Which hasn't stopped some researchers from asking a more provocative question. If there's life there, could there be more than life? While the chemists argued about DMS, a different kind of search was happening in parallel. If K2-18b had a biosphere, even a microbial one, could it, at some stage, host technology? And if it could, would we hear it? The SETI program has been listening for intelligent radio signals from space for decades. In 2025, the Breakthrough Listen project, which coordinates much of the modern search, decided to point its instruments specifically at K2-18b. Given all the attention the planet was getting, it seemed worth checking whether anything artificial was coming from that direction. The results were published in early 2026. They used the Very Large Array in New Mexico and several other telescopes. They covered frequencies from about 544 MHz to 9.8 GHz, a much wider range than previous techno-signature searches of K2-18b. They observed through at least one full orbital cycle of the planet, about 33 days. Across all that observing time, they detected millions of radio signals. That's normal. Our own technology, cell phones, satellites, radar, every radio source on Earth bleeds out into space and gets picked up by sensitive receivers. To find a real signal from another world, you have to filter out all the Earth-based noise. The team used a series of tests to do that. They checked whether each signal persisted when K2-18b passed behind its star, from Earth's perspective. A real signal from the planet's surface couldn't reach us during that window, because the star would block it. Any signal that kept coming through the block was, by definition, local. They checked whether each signal drifted in frequency over time. A transmission from an orbiting planet should Doppler shift as the planet moves toward or away from us. A signal that stayed at a fixed frequency day after day was probably from our own planet or satellites, not from K2-18b. After processing over 20 million signals from the VLA alone, the team found none that survived all the tests. No candidate transmissions from K2-18b. Radio silence at the sensitivity the team could achieve, which was enough to detect transmitters roughly 1,000 times weaker than previous exoplanet searches could find. The conclusion, as written in the paper, was carefully hedged. A null result doesn't mean K2-18b is uninhabited. It could be a world with pre-technological life, like Earth was for most of its history. It could be a world with technology that doesn't use radio in ways we're listening for. Narrowband signals in the frequency range we scanned. It could be a civilization that communicates through lasers, through directed beams, through methods we haven't thought of. Or it could just be a world with no technology at all, or no life at all. What's striking about the result is the contrast it sets up. On the biosignature side, the evidence is ambiguous but ongoing. The DMS signal could be real. The ocean could be alive. On the technosignature side, the evidence is definitively null. Whatever K2-18b is, it isn't broadcasting radio at detectable strength. The combination makes sense. A thriving microbial biosphere does not produce radio signals. It produces gas. DMS, if it's there, is consistent with microbes, not with engineers. Nobody expected radio emissions from a hypothetical Hycean ocean full of sulfur metabolizing bacteria. The SETI search for K2-18b was a thoroughness check, not a serious expectation of detecting intelligence. The radio silence tells us something important, though. Whatever is or isn't happening on that planet, it is not the kind of activity that announces itself across the galaxy. The question of whether any signal from any exoplanet could ever be conclusive is becoming its own debate inside astrobiology. Harrison Smith and Cole Mathis, the two astrobiologists who have been loudest about the limits of biosignature detection, have made an argument that cuts deeper than any technical critique. Their argument is essentially philosophical. It asks whether, given the nature of the measurement, any gas in any exoplanet atmosphere can ever be sufficient evidence for life. The logic runs like this. To conclude that a gas signals biology, you have to rule out all non-biological sources. On Earth, ruling out non-biological sources is possible because we have full access to the planet. We can take samples, run experiments, map the geology, simulate the chemistry under controlled conditions. After 200 years of this, we're pretty confident that most DMS on Earth comes from life. For an exoplanet, we have none of those capabilities. We have a telescope, we have theoretical chemistry, we have models of what atmospheres should look like under various conditions. We do not have samples. We cannot run experiments of the actual planet. We cannot verify our models against ground truth. Without ground truth, any claim that a signal is biogenic is an inference from incomplete information. The claim takes the form, given everything we know, biology is the best explanation. The problem is that everything we know is itself incomplete. There could be non-biological processes we haven't thought of, or haven't characterized well enough. Until we know abiotic chemistry exhaustively, which is essentially impossible, we can't be sure biology is required. Smith and Mathis have argued that this isn't a solvable problem with more telescopes. It's structural. JWST is not a life detector, it's a spectrometer. It tells us what gases are in the atmosphere. The interpretation of those gases as biological or not is a separate analytical step, and their step depends on knowing the full space of alternative explanations, which we don't. Their conclusion isn't defeatist. It's that biosignature detection done responsibly should be probabilistic. You can say a gas combination is unlikely to be abiotic given current models. You can say the probability of biology is non-trivial. You can't say with current tools that you've detected life. That level of certainty requires more than remote spectroscopy can provide. Sarah Rugheimer at York University is more optimistic. She thinks the right combination of gases, detected with sufficient precision on the right kind of planet, could push the probability high enough to be convincing. She lists what she'd want to see: oxygen, methane, water, carbon dioxide in thermodynamic disequilibrium on a planet around a sun-like star in the habitable zone, with high statistical significance in the detection. That's a tough list, but she thinks it's achievable with future telescopes. For K2-18b specifically, the philosophical problem is especially acute. The planet is around a red dwarf, which means photochemistry is unusual. It's a sub-Neptune, a class whose interior we don't fully understand. It has a hydrogen atmosphere, not the nitrogen-oxygen atmosphere our biosignature models were developed for. Every aspect of it pushes us further from Earth, which means further from the regime where our models have been validated. Even granting that biology might be the best fit for the DMS signal, best fit is not the same as confirmed. The gap between those two is where the field is currently living. This is where the loudest voices in the skeptical camp aren't saying the Cambridge team is wrong. They're saying the field needs to rethink what counts as evidence, rethink the thresholds for announcements, rethink how press conferences are handled, rethink what we communicate to the public. Because there's a reputational problem brewing. Kevin Stevenson at Johns Hopkins University Applied Physics Laboratory used a specific phrase when he commented on the K2-18b controversy, the boy who cried wolf. He wasn't the only person to use it. Multiple scientists, in interviews and in papers, have voiced a growing anxiety that the pattern of biosignature announcements, followed by reanalyses, is going to damage public trust in science. The worry is concrete. Consider what the public has seen in the last 6 years. Phosphine detected in Venus's atmosphere. Headlines suggesting microbial life in the clouds of our neighbor. Over the following years, the signal gets questioned, reanalyzed, partially retracted, argued about. No consensus resolution. The story fades from the news without a clear ending. K2-18 be announced with water, methane, and carbon dioxide, plus a hint of DMS headlines suggesting signs of life 124 light-years away. Excitement, coverage, then more data, more scrutiny. K2-18b again with a stronger DMS and DMDS claim. Headlines suggesting the strongest hints yet of biology outside the solar system. A press conference, a revolutionary moment. Then, months later, a reanalysis by NASA walking the claim back. The story, once again, doesn't end with a clear yes or no. It ends with needs more data. From the public's perspective, this looks like a pattern. Scientists get excited, make claims, walk them back. Each cycle erodes some credibility. If the pattern continues, by the time a real, unambiguous biosignature detection happens, if it ever does, the public may be too jaded to recognize it. That's what Stevenson meant by the wolf metaphor. Not that anyone is lying. The scientists making the claims are operating in good faith, within the norms of their field, with honest caveats in the technical papers. The problem is how the claims get translated for general audiences, how the media amplifies them, and how each incremental retraction chips away at something hard to rebuild. Some researchers have suggested structural changes, higher thresholds before announcements, more internal community review before press conferences, a field-wide agreement on what constitutes a biosignature claim versus a preliminary observation. None of these proposals have gained traction as formal policy. The incentives cut the other way. Making a claim generates attention, funding, and institutional support. Being cautious generates nothing. A researcher who announces a potential biosignature gets on the news. A researcher who says, "We observed a signal that requires further study," gets ignored. The attention economy of science rewards drama. There's also a genuine uncertainty about where the right threshold is. 3 sigma is arguably too low historically. 5 sigma is arguably too high, given the nature of exoplanet data. Nobody has agreed on a replacement standard. Until they do, each announcement will be judged on its own terms, with inconsistent outcomes. For K2-18b, the pattern is now visible. April 2025, excitement. July 2025, reanalysis. August 2025, further reanalysis, pushing the conclusion in the same direction. The planet is still interesting. The search is still ongoing. But the moment when the public was told we might have found life has passed, and the quieter follow-ups have done their work. What comes next matters. The Cambridge team has additional observing time approved. More transits will be observed. The combined spectrum will get better. If the signal is real, stronger data should confirm it at higher significance. If it isn't, stronger data should kill it. Either answer helps. Ambiguity is the worst outcome. Ambiguity is what we have now, and ambiguity is what erodes trust. What happens next, concretely, on K2-18b? The Cambridge team has secured additional JWST observing time in the current observing cycle. The plan is to accumulate more transits with both NIR spec and MIRI, building up a spectrum with smaller error bars and better wavelength coverage. If the current signal is a real feature, more data should make the bumps taller relative to the noise. If the current signal is statistical artifact, more data should flatten the spectrum out. The math is straightforward. Noise in transit spectroscopy scales roughly with the square root of the number of transits. Double the transits, and the noise goes down by about 40%. Quadruple them, and the noise is cut in half. The Cambridge team's April 2025 spectrum used 8 MIRI transits. Doubling that brings the statistical precision up meaningfully, though not enough to convert a weak signal into a strong one, if the underlying feature isn't really there. Several competing teams are also planning observations. The community has converged on K2-18b as a test case, which means multiple independent pipelines will be processing the same new data. If the next round of spectra shows the DMS signal emerging more clearly in independent analyses, the consensus will shift toward the biological interpretation. If the signal stays weak or disappears, it will shift away. There's an interesting feature of the data-taking process itself. J-BioST's sensitivity to any particular molecule depends on where in the spectrum you look. Some wavelengths are dominated by water, others by methane. The narrow windows where DMS and DMDS have distinctive features are limited, and extending observations to those exact wavelengths is what the Cambridge team has prioritized. The instruments themselves are also evolving in how they're calibrated. JWST has been operating for about 4.5 years now. Understanding of its systematic noise profile has improved significantly over that time. Data processed with the most up-to-date calibration often looks cleaner than data processed with earlier tools. The 2023 and early 2025 K2-18b spectra were reprocessed in 2025 using improved calibration, and the reprocessing changed some details of the features. Future observations will be calibrated with even better tools, potentially reducing the ambiguity. There's also a case for patience. Exoplanet atmosphere research is young. JWST is the first telescope capable of doing this kind of work on small planets. The community is still figuring out best practices. How to combine data, how to handle systematics, how to report results. Some of the heat around the K2-18b debate is the heat of a field growing up in real time. Niku Madhusudan has said publicly that if additional observations do not strengthen the DMS case, the team will accept that. He has also said that the current ambiguity is not a failure of the science, but a reflection of where we are in the capability curve. The data we have is already remarkable. It was unimaginable a decade ago. The fact that we can even have this argument is a triumph of telescope engineering. The next set of K2-18b papers will likely arrive over the course of 2026. Data that's being collected now, pipelines that are being refined. If the story moves decisively in either direction, it will be the story of the year in astronomy. Whatever the outcome for K2-18b specifically, JWST alone may not settle the biosignature question for exoplanets in general. The telescope has limits. Going further requires new telescopes, and those are already being designed. JWST was designed in the early 2000s as a general-purpose infrared observatory. Exoplanet atmosphere characterization was one of many goals, not the primary driver. It turns out to be the telescope doing the most important work in that area, because nothing else of comparable capability exists. But if you wanted to design a telescope specifically to detect biosignatures, you would build something different. NASA and the astronomy community have been doing exactly that. The next major space telescope in the planning pipeline is the Habitable Worlds Observatory, or HWO. It's a direct successor to concepts that emerged from the 2020 Decadal Survey, the astronomy community's priority-setting exercise. HWO is designed from the ground up to look for biosignatures on Earth-sized planets orbiting Sun-like stars. The key capability HWO will add is direct imaging with a coronagraph. Instead of watching a planet transit in front of its star and reading the atmospheric spectrum from tiny differences in the combined light, HWO will physically block the star's light and directly observe the planet as a separate point of light. That's a completely different kind of measurement. It works for planets that never transit. It works for getting cleaner spectra. It gives access to reflected and emitted light from the planet itself, not just light passing through its atmosphere. HWO is not expected to launch until around 2040, best case. It's early in development, but its design goals are explicit. Characterize the atmospheres of at least 25 Earth-sized planets in their habitable zones, with biosignature-relevant precision. That's the ambition. Whether it's achieved depends on budgets, politics, and engineering decisions still being made. On the ground, the Extremely Large Telescope, or ELT, is much closer. Being built in Chile, scheduled for first light in 2028, the ELT will have a primary mirror over 100 feet across. That's 4 times wider than JWST's. The resolution and light gathering capability will be transformative for direct imaging and spectroscopy. The ELT won't go as deep into the infrared as JWST can. Earth's atmosphere blocks some of the crucial wavelengths. But for other biosignature work, it will outperform any current telescope by a wide margin. The 30-meter telescope and the Giant Magellan Telescope are 2 other large ground-based observatories in development. Each brings its own capabilities to the search. Together, the next generation of facilities will multiply our observational power by large factors. For K2-18 specifically, the question is whether any of these upcoming telescopes will do better than JWST. It's the hard call. K2-18b's star is dim, so ground-based observations are harder. The ELT might be able to improve certain aspects of the planet's characterization, but not decisively. The sub-Neptune size range and the hydrogen atmosphere may always be challenging. For other sub-Neptunes and Earth-sized planets, HWO in particular will be revolutionary. A direct image of a planet around an Alpha Centauri-like star, showing its reflected light spectrum, would be the most convincing biosignature attempt ever made. If life is out there in the closest stars, HWO might be the telescope that finds it. The question of life elsewhere is not going to be settled by one telescope or one observation. It's a cumulative project, built up from many detections, many reanalyses, many planets, many instruments. K2-18b is one point in that curve. It may or may not turn out to be a real biosignature, but it's part of the work that is building the capability to know. The search doesn't stop with K2-18b. The queue of candidate worlds is already forming. K2-18b gets the headlines, but it isn't the only game in town. Since the Cambridge team identified the planet as a priority, several other worlds have joined the list of potential Hycean or hydrogen-rich habitable candidates. One of the most intriguing is TOI-1452b, discovered by NASA's Transiting Exoplanet Survey satellite, TESS, in 2022. This is another sub-Neptune orbiting a red dwarf about 100 light-years away. Its mass and radius are consistent with a world that could be up to 30% water by mass. That's an extraordinary amount, far more than Earth's roughly 0.02%. If the water is present in liquid form under a hydrogen atmosphere, TOI-1452b could be a Hycean candidate. JWST observations are planned, and if DMS or other biosignature gases show up there, the debate will expand. Another target is LHS-114OB. This one is a super-Earth, not a sub-Neptune, but it sits comfortably in its red dwarf star's habitable zone. In 2024, JWST spectroscopy of LHS 114OB was consistent with a hydrogen-nitrogen atmosphere, though not definitive. The planet is denser than K2-18b and likely more rocky, which opens a different class of biosignature possibilities. Not Hycean, but potentially habitable in more Earth-like ways. TRAPPIST-1's 7 planets remain under intense scrutiny. Several of them are in the habitable zone of their red dwarf. JWST has observed a few of them, and the results so far have been underwhelming. Thin or absent atmospheres on the inner planets, which suggests the red dwarf's flaring may have stripped them long ago. The outer TRAPPIST planets, particularly TRAPPIST-1e and F, are more promising, and observations continue. Farther afield, the Roman Space Telescope, scheduled to launch in 2027, will not be a biosignature machine itself. It will conduct a massive microlensing survey that will discover thousands of new exoplanets, including a substantial fraction of Earth-mass planets at orbital distances similar to Earth's. Many of those will become targets for later characterization by HWO and the ELT. There's an interesting pattern emerging from the current crop of candidates. Most of the planets where we can detect biosignature gases with current telescopes orbit red dwarfs, because those planets transit deeply and often. But red dwarf planets come with the photochemistry problem, the flare problem, and the general question of how habitable worlds around small stars really are. Earth twins around Sun-like stars, the canonical search targets, are harder to observe, but arguably more likely to host straightforward biology. The field is trying to have both. Use the accessible red dwarf planets to develop techniques and probe the limits of biosignature interpretation. Save the harder Sun-like star planets for when HWO is ready and we can do direct imaging. The two approaches feed each other. Lessons from K2-18b and its cousins will shape how we interpret whatever HWO eventually sees. The landscape is filling in. A decade from now, the list of planets with JWST biosignature candidates will probably include a dozen or more. Some will hold up to scrutiny. Most will, like K2-18b so far, remain contested or fade. A few might survive into the age of HWO with their biosignature interpretations intact, and those will become the priority targets for direct imaging. Somewhere in that list, there might be a real one. The question is which. Back to where we started. 124 light-years from Earth, in the constellation Leo, there's a planet called K2-18b, and a scientist named Niku Madhusudan, who said it wasn't natural. Nearly 2 years have passed since the April 2025 press conference. The evidence has been probed, reanalyzed, and contested. The biosignature claim has been downgraded, though not killed. The planet remains under observation, and the next round of data is being collected. Was it real? Probably not. That's the honest, boring, scientifically defensible answer based on the evidence available today. The signal is weak. The statistics don't survive rigorous treatment. Alternative explanations haven't been ruled out. Independent reanalyses keep landing in the same place. Insufficient evidence for DMS, insufficient evidence for life. But probably not is not, definitely not. The signal hasn't been proven to be noise. The biology interpretation is still the most elegant fit for one specific set of assumptions, and the Cambridge team may yet be vindicated by future data. If the next set of observations strengthens the DMS case at higher significance with independent replication, the story changes. If it weakens it further, the story ends. Either way, something bigger has happened through the K2-18b controversy. The field of exoplanet biosignature detection has come of age in public. The questions at stake: what counts as evidence? What thresholds are appropriate? How to handle ambiguity? How to communicate with the public? Have been forced into the open. Astronomers are having real arguments about real problems, in real time, visible to anyone paying attention. That's healthy. Decades from now, when a confirmed biosignature detection finally happens, if it does, the framework for interpreting it will have been forged in controversies like this one. The mistakes being made now, the overreaches and the pushbacks, are how the field learns. The boy who cried wolf worry is legitimate, but the alternative, where nobody ever announces anything until absolute certainty, would be worse. Science advances through claims and counterclaims. It always has. What the K2-18b story really tells us is how close we are to answering the oldest question humans have ever asked. Is there life beyond Earth? For most of human history, that question was purely philosophical. In the second half of the 20th century, it became technological. We built probes, we searched Mars, we listened for radio signals. In the 21st century, it's become observational. We can now point telescopes at the atmospheres of planets around other stars and read their chemistry. Not perfectly, not conclusively, not yet. But the fact that we can have serious arguments about whether one specific molecule in one specific atmosphere of one specific planet, 124 light years away, represents biology or not, that's something. 50 years ago, the question of life on a distant exoplanet was science fiction. Now it's a working scientific debate with spectra and statistics and teams of researchers submitting papers back and forth. The next telescope will do better. The one after that, better still. Somewhere in the next few decades, the signal will either become unambiguous or the hypothesis space will narrow enough that we know what kind of biosignature we're looking for. K2-18b may turn out to be a footnote, or it may turn out to be the first. We can't tell yet. What we can tell is that we are, as a civilization, in the middle of the longest and strangest search humans have ever undertaken. The sky is full of stars, around most of them, planets. Around some of those planets, atmospheres. In some of those atmospheres, maybe chemistry that shouldn't be there unless something alive is making it. One of those atmospheres right now is K2-18b's. We're reading its air like a letter written in a language we're still learning to speak. The words are faint. The handwriting is strange. We think one sentence might say, life. We aren't sure yet. Keep looking up. The answer is coming.